Pour vous éclaircir un petit peu sur un sujet d'actualité tel que l'optimisation des problèmes, d'ailleurs combinatoires, en utilisant des techniques de machine learning. Le français s'arrête là. Et maintenant, donc, on passera à la présentation de ce genre de problème, mais en anglais. Okay? Okay. So what I would like to talk to you about today is to give you some flavor. I am not giving you a lecture, a detailed lecture on how to apply deep learning and optimization problems. But I will give you some flavor. I give you a universal way of doing, of basically modeling optimization problems using deep learning, one of the machine learning techniques. Okay? But before that, my colleague earlier on, actually, he gave you very good flavor on the deep learning, and he gave you very, very promising applications. I know maybe you saw me working on a computer over there, maybe tidying up my slides, but I heard nearly everything. So it was very, very interesting, and as well, it's a future. We believe it's future. And they give you some examples before, again, as flavor. Before I will dive into the details, how to apply them into optimization problems. So before that, I know maybe you are sick of this slide. You see it every day. I see it every time I present on my talks all over the world, because this is the mission of my university and I have to do it, right? So Insight Center for Data Analytics, this is one of the biggest centers in Europe who created it. I am one of the researchers there. I'm a principal investigator, and as well I'm principal investigator of Consus, which is basically the application of machine learning to precision agriculture, how to optimize the agriculture processes, and as well the yield using machine learning techniques, or data mining or data analytics, basically. So I am professor in computer science. I'm professor of computer science in computer science school. I am from University College Dublin. The difference, it's not University of Dublin, it's University College Dublin, because University College of Dublin is one of the competitor, is Trinity College, right? I am from University College Dublin, one of the biggest university in Ireland. The insight expertise, again, I may repeat it. By the way, we have positions for postdocs and for PhD students. I am here. I'm very happy to take students. I'm very happy to take postdocs. But you have to show the money. You have to show that you are very good. So if you are very good, I'm very happy to talk to you. So basically what we do in the center is very simple. We do some basic and applied research, and we do collaboration projects. Of course, for example, Insight is one of the examples, because we have more than 15 companies, private companies, and we have about 8 collaborators, other universities, other research institutes. The combination of this is one of the most important things as well. We contribute to the economy by creating campus companies. Ah, yeah, that's good. We have, Doesn't matter. I'll move, I'm okay. So we have spin-off companies. I'm personally involved in 2, and currently we have one just about taking off. Basically that's the whole idea. The whole idea is the government gave us money. They gave us a lot of money, and they want to see the fruit of that money by creating companies, by seeing the results coming out of this. Again, the vision is very simple. Is basically we try to empower, well, or maybe create, if you want, a data-driven society, and we want to understand it, and we want to give them the best possible way how to behave within this, the whole, digital world. Again, my expertise, everything you can see in the red, that's what I'm doing within the center. I'm doing real-time data. I'm doing multidimensional data, very, very high multidimensional data. I'm working as well in personal data in the healthcare area. This is all the data, more or less. I use even cybersecurity or forensics. Personal sensing. Of course, we have. I'm developing some personal sensing, and then of course the whole thing about machine learning and statistics. That's where we develop new techniques of data analytics. My biggest hot topic at the moment is what we call big machine learning. It's like big data analytics. In terms of the results, we have more or less a spectrum of decision making, such as, for example, finding evidence, scalable solutions, decision making, and timely decisions as well. So that's more or less my expertise. The insight, I mentioned the insight. This is, again, we had 88 million. This is the first wave, what we call Insight 1. We get now another 59 million. You can say why we had less money now than before. We have less money now because now we have the infrastructure. The infrastructure is there. Now the money of 59 million is for to do research only. And we have many research, by numbers, as you can see. Well, that stops here, okay? If you've seen it before, that's okay. If you haven't, it gives you a good an introduction for it. Now, let's talk a little bit about this data analytics, data mining, or machine learning in general. I will start with you with very basic application, which started a long time ago, which is basically digit recognition or pattern recognition or whatever you call it, character recognition. Handwriting recognition is not easy, right? But now we developed very, very good techniques. This is one of the, the screen you can get, you can get online. And you have different varieties of writing the numbers. And the whole idea is to recognize it. If it's 4, you have to recognize it as 4, and so on and so forth. So the deep learning is used actually to recognize digits. And of course, there are many techniques used as well as part of machine learning techniques. If you take, for example, the 8, well, it's an image. If you take it like this, it's an image 28 by 28 pixels. And it's represented by a certain number of grayscale values, okay? Now, well, we can use, some simple description, either, for example, percent pixel field or symmetry. For example, you are looking for symmetry, and usually we have many of the characters which basically present this symmetry there. If you take, for example, here, I have symmetry, maybe we're looking for symmetry in the 8, and I use percent pixels filled in, for example, what it looks like as 7, okay? So then, if we try to print this, and earlier on I will give a very good example. If you take an image, you look at in whatever the one, either percent pixels filled or symmetry, you will see something there. There is no symmetry in 7, but there is symmetry in 8, right? And so on. So we know how to build these systems, and actually very, very simple systems, but we know how to do them. And this is why even we know how to discriminate between these two, right? If, for example, for the probability of being, for example, getting this as 8, we have as well tools to measure it and calculate it as well. Now, if I look at, for the certain image here, you will see it's not always a very, very clear discrimination between what you can see as field, as picture, as a pixel field or symmetry. It's a little bit very, very fuzzy. right? Of course, then the other problem is you have to get it out of the context. For example, here we have 28 by 28, which basically gives you 784 pixels. Can I use the same techniques as used with the smaller image as well? Okay. But yes, we can. We can define and we measure this, and we know how to do it. Basically, at the lower level representation, we can use a vector, a vector feature here, for example, because we are using picture 28 by 28, and we can define it as a vector feature of 784, which we can basically then feed it within a network and throw it what you can find. Of course, we have all the spectrum of each of the letters of characters. And then, of course, then it's much easier for a network to learn because now we have, well, you build something like that with certain number of layers. And at the end, you put the spectrum of 8 here. You will have a result here at the end as something which is basically tells you is 8, right? So we know how to do that. And deep learning networks are actually doing very well. And that is even I give you even another good news. Yeah, we can of course build all of the. We master this now. We know even if each layer what each layer is doing really. You know, either for example as a subsampling or convolution or feature extraction and so on and so forth. Deep learning, they can recognize these pictures. That's something incredible. They can recognize these. And this is the curve, you know, if you print how deep learning techniques, in other words, more as machine learning, network techniques, they evolve over time. This is 2005 until 2015. You see the error going down as we go along. So it means we improve them more and more until we get the error a little bit down. So now I have a question for you guys. What level of error do you think human can achieve in this task? I give you pictures and you tell me what it is. What's the percentage do you think? Huh? Okay. Who is for, we start from the top. Who is for 1%? Who is for 5? Who is for 15? And the last one? And obviously there are people without opinion. That's not good, isn't it? Now, well, this is the answer. The answer here, this is what human can do. Yeah, we can recognize a lot, but actually we can make an error of 5%. But deep learning now, in 2015, not a long time ago, just about 3 years ago, we are going below the 5%. It means we are getting at the 99%. So the machines, in other words, the machines are doing better than us. Yeah, that's incredible. And we have this, we use this possibility even to do it, to have a spectrum of application of this. For example, if you take a monitoring patient pain, just to monitor, patient pain, we have, of course, we have the devices, we have, and we define, the stiffness when you, for example, you are sleeping in one side and then you didn't move for quite a while, and then when you move, you have a pain, the pain in the evening, in the morning, and so on. So if we take this spectrum and we put it on a screen, you will see something like that. So basically here you have the daily basis, and then here you have the hours. For example, here we take between 6 p.m. until the following day, 6 p.m., right? And you can see what, for example, here it's 6 p.m., that's okay, and then here until, 6, 7, 8, 9, 10, 11, 12, here by midnight you can see, how it's actually clear. And then we come back here. I need to look on my screen because, which is basically until 7 a.m. in the following day. And you can see, then again, there is a change. in the thing. So we can monitor this, and we can actually precisely, control it, automatically. This is, well, in other words, what we're doing. Well, we do algorithms. We have the data. In one side, we are building algorithms. Another side, we have the data, because this is the only, maybe, the era where we have algorithms and we have the data. In the past, we have the algorithms, maybe. We didn't have the data. And then, of course, we have as well the hardware. It's very, very advanced. And we have applications. The Google, the Netflix, the Facebook, the Twitter. You have a lot of applications. And deep learning is responding positively to that. So it can work. It can work at a very, very large scale with high level of accuracy. Again, you've seen this maybe slide, in the first day. Yeah, deep learning is just one technique of machine learning, and as well as which machine learning is one approach of artificial intelligence, because we have different ways of seeing it. So now, for example, if I focus here, this area here, we can recognize, we can organize, we can control, we can generate. If I focus, for example, on recognizing and generating, yes, we use it today. If you take, for example, Google or any chat, applications, you say, would you like to? And then you see you have propositions here. Chat, C, B, right? And you can choose it, right? It's daily. You think it's easy. It's not easy. There is something there behind that does something there. So here, again, if I go back to the last slide, recognize and generate. Here, it recognizes semantically, would you like? It knows what it means. And then it generates something. It suggests you something. And that's really powerful too, right? Would you like to, right? And then, again, here. Now we can analyze this on the fly, right? And behind this, as I said, I will not go into my colleagues, he spent 3 or 4 hours already explaining this. Yeah, well, there are neural networks behind it, and there are different architectures of these neural networks going this. And a recurrent, or what we call, recurrent neural networks are alternative of deep learning approaches to handle streams of data, like such as speech and text and so on. So they are, all what I showed you before, these recurrent are very, very efficient in doing this. Now, the other question, would you read a novel written by a computer? Well, maybe you don't have the answer because you never tried, right? Well, I did. It was pleasant. Believe me, it was pleasant. Well, the only thing is, how independent that novel from the mind of a human, because those algorithms were written by humans. Well, for example, here, please, when you get my slides, go to this and have a look at it. I will not say anything because that's a computer generation, pure generation. Now, I show you something. How can I stop it? I show you something that deep learning is doing. And if you see, have a look at this video now, a few minutes, and you see how precise the movement is, how precise the equilibrium of things. And there are even areas where actually human will struggle. For example, walking on snow, and an area which is very, very steep. We cannot control ourselves because maybe we're not trained and so on. You see this robot here, which is actually, it's not in 2017, it just released. Have a look now, and you will see how good is this robot. Very precise in stopping. and how he's taking the equilibrium when he turns. See this now. Even the universal forces don't take him out. And see this? And he can take, objects without breaking them. Take the stairs. And see. And he stops on right time. See this? And now see how he jumps? Precise. The algorithm that manages this is a deep learning algorithm, and nothing else. Right, okay, we move on. Now, I will give you, from now on, I'm not going to tell you to basically to learn. Well, there are a few things you have to learn, unfortunately, because it's mathematics. But what I'm giving you here, giving you a general way of trying to build a deep learning, a neural network in general, to solve some of the common problems. But maybe your teachers or your lecturers, your professors taught you to do it with simplex or dynamic programming or something like that. This is an alternative solution to solve them quicker and actually even in better way. So again, the neural network, a neuron, an artificial neuron, it's a very simple concept. You've seen it a few minutes ago. You have just a set of inputs. You have some weights according to these inputs. You have some function sum, and then you have some biased, threshold here. And then, of course, you will put through the output through what we call, activation function, right? And you obtain a result called VI, which is basically between a certain range. You can control with your activation function, most of the time 0 and 1. Right, and then from this concept, we build a complex structures, right? Something like that. All of these little, circles there is a neuron. And then, of course, you have certain topology and certain structure of building them. The first one is basically multi-layer. We call it deep learning, basically, if you have more layers there. But you have different, for example, here is self-organizing maps, neural network. Here you have some recurrent, and you have different topologies. And those topologies, depending on the problem, depending on as well the way you want things to be learned and the problem to be solved. Right, I mean, that's more or less the concept here, and I'm not going into this before because my colleague before, he gave you a lot, information about this. Now, if we want to solve an optimization problem, I will start with a very simple one, linear optimization problem. I call it LOP. So what do you have? You have a function f of x, which is sum of ci xi, right? Very simple, it's linear, subject to certain linear constraints as well. Sum of ai j xi is equal to bi, with some constraint here saying x1 and xn are positive, and if you want to write it in a linear, in an algebraic way or a vector way, if you want, if fx equals ctx subject to ax equal b. Right. So if we take this problem, we can see this problem as searching through a vector space. Basically, this problem has a space of solutions, right? Feasible solutions, and the idea is to try to find which is the right solution, which is the best solution within the whole space. Okay. So this problem here, if we look at the possibilities of solutions that can be returned, you can have a unique solution. Obviously, that's Maybe sometimes that's the most desirable one. Or you can have multiple solutions, what you call non-unique solution. You have many. Or some unbounded solution. You have certain boundaries, but anything which is below this, it's fine. Beyond that is wrong. Or the other possibility is non-feasible. So there is no solution. So if you take the last two in the applications on science, they are unlikely. And they are unlikely to build a problem with no solution or with an infinite number of solutions, just only bound, because it's not really interesting. So in mathematics, you can have those problems, but actually in general, when you have them applied in real life systems, when you build a system like this, more likely you have solutions. They might not be unique, but they are finite, and most of the time we are looking for the best solution. Now, how do we solve, how do you use neural network there? Actually, it's very simple. What we want to do, we want to build this energy function, or this function defined as an energy of an unconstrained optimization problem. So in the beginning, when the problem I showed you before, here is what we call optimization function with constraints, subject to a certain number of constraints. So the idea is to transform this problem into unconstrained optimization problem. So basically, you optimize a function, let's say, rather than having constraint with it, right? So the way you can generate a neural network from it is use, for example, what we call Lagrange multiplier method. So basically, you define this energy function as your cost function plus a certain what we call a penalty parameter. So this is a penalty. So k divided by 2, this is a parameter. Ax minus b, this is basically your matrix of your constraints, and so on. So we have this in the Lagrange. If you write it, this is what you get. I'm not asking you to learn the Lagrangian. You can take it as is. We have two forms. We have the form of E1 without what we call, the difference between E1 and E2 is this only parameter here, alpha lambda t lambda. This parameter is introduced for stability of your equations, of your solutions at the end. So we believe, and mainly when you use a neural network to solve the problem, this one here, it plays a very, very major role in getting stable solutions. So what we do is very simple. We believe that the equation, what you need an equation of motion. X at time t plus 1 is equal to x at time t minus something you multiply by the derivative of the energy function, right? So that's the equation of motion. Then we need to calculate the partial derivative of x ex. So this one here, a partial derivative of L2 of x lambda divided by delta x. You can just do it, from the other equation, and you will find something c plus at, I transpose, multiplied by k or plus lambda, and or is equal to ax minus b. Just because if I have to write everything there, you will not recognize anything. So that's basically simplified there. So, and then the same equation, if I do the derivative, in relation to the lambda, you'll find or minus lambda, alpha lambda. So then, as I said, the equation of motion is if xi at time t plus 1 or at iteration k plus 1 is equal to xi at time at iteration k minus uk, which is basically the learning rate, multiplied by the derivative, the partial derivative of the energy function, right? So basically, and this is of course then for lambda. All these parameters are positive as well. So if I use this equation of motion from here, I can generate straight away the architecture of the network. That's it. So if I program this, I'll find my solution. The only different maybe in this architecture, as you can see, I added, this set to -1 is delay element to allow the delay because you are doing it over time, and you make sure that you are not generating this, in synchronous fashion. You need just to generate it in synchronous fashion, and therefore you may have to add some elements in the architecture to represent those delays. So this is the equation of motion designed as neural network. As you can see, it's a recurrent neural network. It's basically more or less more close to what we call Hopfield networks. It works, and you will get your solutions after a certain time. If I give you an example of such systems, if I take f of x, x1, x2, well, 0x3, 0x4, 0x5, because I simplify this, I cannot write everything in the slide. Usually you have f is equal to x1, x2 subject to constraints minus 2, x1 plus x3 is less than 3. Then x1 plus 3, x2 is less than 16. And then, of course, for x1 plus x2 is less than 20. Here I transform the inequality constraints into equality constraints by adding x3, x4, and x5. So because if I remove x3, I will have x2, x1 plus x2 less than 3. So what I want an equation. Okay, so then I add x3 to have equal to 3. Is that okay? So it's very, very simple. I transform inequalities into equalities. So then I will be exactly the same problem as here, as here. Then basically I can apply my network on this. So when I have this, I run it. You run it for a certain number of iterations. Very, very quick, by the way. All the solutions, they convert very, very quickly to basically more or less near optimal solution. It's very quick, and that's very, very handy. Now, I can show you another way of defining your neural network using inequalities in this case. Okay? We take the same problem. Rather than having equal here, you'll have less or equal b. We can do that as well. It's the same way. You use a Lagrange multiplier again, but this time I will define this. The k has very, very important role here. The energy function of xk is equal to ctx plus k is sum of some function called phi of the constraints, right? This function phi is basically more or less a canonical symbol. It takes 0 is equal to 0 if or I of x is less than 0, or it's higher, whatever the value you find if x or I is equal to is higher than 0. So, and xi of x is basically the ix equal b, minus b, sorry. And of course the variables are positive. So we do the same thing. I can use my equation of motion, which is basically xk plus 1 is equal to xk minus mu delta xk divided by delta x. I do my derivatives. And then, of course, I can choose, of course, the psi of v is the derivative, well, is the derivation of the phi v of v. And I can choose this function here, half of v squared. Why do you think it suits me to take phi is equal to v squared? Because it's quadratic form, and they know at the minimum I will have, yeah, exactly. It's very, very simple, right? So then my equation of motion is very simple. Xi of k plus 1 is equal to xi of k plus mu I delta xk divided. Following this? And now all what I need is divide my, okay, there are alternatives. The phi of v, you can, here I choose it, for example, to be half of v squared, but actually you can choose the phi of something like maximum, another function. It's not necessarily the same function. right? But you have to define the network accordingly. Then I can build it, right? I can build it. I can calculate the values. These are my BIs, and then I have my derivative function, and then I have my sums. I have my learning rate, and then of course I have my activation functions, and then of course you do a certain number of iterations, and it converges to the right, well, near optimal solution. Well, guys, I'm not doing everything for you. You have to do something. So, for example, for the quadratic form, if I have, for example, a function f of x, which is of the form of xtqx, right? The idea then is to basically maximize or optimize in general f of x of ctx plus something which is not linear, obviously, subject to a certain number of constraints. Here, linear constraints for the moment, but we can work step by step towards non-constrained linear constraints as well. You can do this. What I want you use the same principle of gradient descent and Lagrange multiplier. Try to do that and generate the equations for this and actually build the network yourself. I will give you an example for this because I choose a function here. This is a function I want to, maybe I want to optimize, and I generate something like that. Okay? So it means when you do your exercise and you try to do the derivation and everything like that, your equation of motion has to give you this kind of thing. So it means you have already a solution for this. If I want to maximize something like that, x1 plus x2 minus x1 square minus 3 x2 square, subject to some linear constraints like this, again, of course, I use the same method, gradient descent, to generate my solutions. I can build a network for it as well. So here, for example, as you can see, I have for k equals 0 and I have for k equal 1. In here, one thing which is very, very interesting, there is an oscillation about x3, x4, and x5 because they are friction variables which basically I introduced. But the x1, x2, more or less, they behave more or less the same way. So they start a little bit, fluctuating, and then after that, they go, towards, the optimization part. And the same thing here. So the solution for this problem for x1, x2 is 4 and 4. Actually, the solutions we found after some 3,000 iterations, more or less, it's exactly 4.0053, and then for x2, it's 3.99963. So more or less, it's there. So it's very quick. And we found a solution for this. Actually, very, very handy, and we are within the 99 point something percent of accuracy. That's it, guys. I'm not giving you more. All right? As I told you, I'll give you a flavor. This is, by the way, as a universe. Well, it's a unified way of solving optimization problems using deep learning approach. Any optimization problem, you can formulate it like this by calculating your derivatives and so on and so forth.